Hello everyone, today we'll talk about the problem delete nodes and return forest. We're given a binary tree where each node is identified by a unique value, and we're also given a list of node values, and that list is a list of nodes that we should delete from our binary tree. Of course, after removing some nodes, our tree may, and probably will, decompose into multiple trees into a forest, and we have to return that forest in an intuitive way, so as just a list of roots of all the trees in our forest. So in other words, we can imagine any arbitrary binary tree. Let's say that we remove this node, we remove this node. So what happens? Well, we just remove them. So this one doesn't exist, this one with its adjacent edges doesn't exist. We're left with a forest of 3 trees, and we have to return this, and this, and this, all on a list. Often in problems like that, it's natural to think about a recursive solution. So let's imagine that we have our root and the left and right subtree. So if we first recurse on those subtrees, we can assume that everything that happens deep here and deep here is already taken care of. So nodes were deleted, new roots were added to the list, and now in the vicinity of this node we have our left and right child. So maybe they have to be deleted, maybe they don't have to be deleted. We can assume that when we recurse on those trees, then the recursive function will either return none if the node is supposed to be deleted, or it will return this node with adjusted children, of course, if that node is not on our list. So we know if left and right children are supposed to be deleted or not, and if our root is supposed to be deleted or not is the final decision that we have to make. If we don't delete our root, we just adjust left and right child to be what was returned by our function. So maybe if some of them disappeared, then here we have none. If they exist, we have this adjusted value. And if our root disappears, then this is the point where if one of our children is still okay, then it becomes new root, because it loses its parent. So for our children that are not none, in that case we put them on the list of new roots, because they are for sure a root. And at the very end we also have to check if our original root is on the list or not, because so essentially the return value of our function on the original root, to know if we should put it on the list of roots or if we should omit it. And that is the whole philosophy. Of course, since we're given a list, then the first thing we should do is to change it to something that can support fast lookups. So for instance, let's see a set instead of a list, because for a set we have essentially constant time lookups if some node is to be deleted. And also, we'll of course keep a list of all the nodes, at the end we return it. And the recursive helper function looks at the tree that is passed. If that tree is none, of course it just returns. And now we adjust the left and right child of the current node to the result of recursion on those trees. And now, if we have to delete our value, then for both our children we check if they are removed or not, and if they weren't removed, they are now a root in our forest, so we add them to the result. And we return none because we have to remove our root. Otherwise, our root is not to be removed, we return it. And now we run this function on the original root, and if that root is not to be removed, we add it to the list of roots. And that's it. A simple recursive algorithm.